So we're going to talk today about rectangular components of a force. I said it's very easy topic. As long as you guys remember your concept of sine, cosine, and tangent. That's all you need for this, basically. So we can review that a little here. What I'm showing here is the rectangular components of two red forces, the force F here. Rectangular components are called the components that form 90 degrees between them. So this is the y-axis and this is the x-axis. So in both cases, they form 90 degrees. That's usually the case for the x and y-axis. So if those two directions are 90 degrees, that's what we call rectangular components. Let me change the color of this. It's nice here. So remember what we said about components in previous class. The two components of a vector are two vectors that if you add them together, you get as a result the original vector. So in this case, the components Fy and Fx are two vectors that if you add them together, you get the original F. You see here that it's kind of like doing the parallelogram method to do the summation. So you draw the parallel lines to the direction. So this line is parallel to this one, and this line is parallel to that one. And then at the point where the two lines meet, you do the point, the head of the vector, and at the tail of the vectors, you put the tail of the resultant. So you draw the diagonal of that parallelogram, and then you get the summation F, right? So now we know the vector Fx plus vector Fy is equal to vector F. This is a way to denote vectors with a little arrow on top, like a little hat in the shape of an arrow, right? So these Fx and Fy are components of the vector F. So how do we get the components of the vector F? So numerically we use the sine and cosine. The sine and cosine, let's go here. The sine and cosine functions in order to get it. So let me put it here. If this is the angle theta right here, then we can now let's define here. Hold on. Let's define here these unit vectors I and j is in order to set up some kind of convention here. I is a vector of magnitude 1 and j is a vector of magnitude 1. These vectors are I in the direction of the x-axis and j in the direction of y-axis. So, so this allowed us to write the vectors in a nice way where, for example, if I have here the vector Fx, I can express the vector Fx as the magnitude of the vector, which is just the scalar. How long is that arrow, right? Is this Fx, like in italics, multiply that the vector I. You will see sometimes that the vectors are represented by bold characters. You see the I is kind of like darker here. So if I multiply the magnitude by the vector of magnitude 1 in the direction of the x-axis, I obtain the vector Fx, which is a vector in the direction of the x-axis with a magnitude equal to Fx. I can write it in another way like this. Magnitude of vector Fx is equal to Fx. Another way to express the magnitude of a vector is to write the vector with the little hat and with these bars. This means magnitude of the vector. Another way to do it is just to write the magnitude. This fx is magnitude. This is just a scalar. A scalar. Just a number. If I'm going to remove the bars, if I remove the bars, then I have the vector. Then I will have to put here the vector I. And it's usually also, instead of the arrow, to put the little hat like this. That's another way to express the unit vector I. So the magnitude of the vector I is 1. So let's repeat here. This vector fx can be understood as the magnitude fx without the hat multiplied by the direction, which is the vector I, a unit vector in the direction of the x-axis. Then the vector in the direction fy can be understood as the magnitude of the vector multiplied by the direction. This gives you the magnitude, this gives you the direction. And the magnitude, you calculate the magnitude using your trigonometric functions, cosine and sine, these two expressions that you have here. Then you can express what I said before, the vector f, the vector f is equal to fx plus fy. Written in another form will be this here. When you
Professor, can you move your screen up a little bit?
The screen.
It's cut, the last equation there is cut off.
This one like this, like that. When you are write down with your hand, it's difficult to make the difference between bold and regular font. You cannot write something like this. So you say fxi, you don't see that the I is bold and the fx is not bold. So when you are writing by hand, in order to be more specific about what is a vector and what is a scalar, then the vectors will have the hat, or this will be a vector with the hat, or with the little hat like this. This means a vector, this means a vector. And if you want to be very specific about the magnitude of a vector, for example, fx, the magnitude, then you would go like this. That's very specific about the magnitude of the vector fx equals to fx. See? So we'll be using both nomenclatures over the semester. Whatever is more clear in a given moment, but it usually doesn't lead to any confusion. But the point to be made here is that the components can be calculated using the sine and the cosine. So the magnitude of the x part here, fx, is equal to the magnitude of the vector multiplied by the cosine of the angle that I have down here. And same thing for the y component. It's going to be the magnitude of the original vector multiplied by the sine of the angle theta. This expression here, fy equals f sine theta. All these equations here are scalar. These are scalars. These are just numbers. Everything is a number here. Fx is a number. F is a number, is the magnitude of f. Cosine theta is, of course, a number, a scalar. This fy is the magnitude of the y component. This f is the magnitude of the diagonal vector here. And sine theta is, of course, a scalar. All of these are scalars. In this equation here, we are mixing here vectors and scalars. Let's point out, this f is a vector. This fx is an scalar. This I is a vector. This fy is a scalar. This j is a vector. Vector, scalar, vector, scalar, vector. If we want to write this by hand, which you cannot do bold font by hand because it's kind of impossible, then you will do something like this. F vector is equal to fx. If you want to be very specific, you will do like this. See? The magnitude of the vector fx multiplied by the unit vector I plus fy. But if you want to be sure that everybody understand what you mean, you say this is a vector, but I am taking the magnitude by putting those bars there, multiplied by the vector j. This will be the best way to be very specific, no confusion, everything understands very clearly, an equation of vectors and scalars together. That will be the best way. And then in the next line, you will do something like, let me erase this. And then below this equation in blue, you will write this explaining how you calculate the magnitude of those vectors fx and fy, the magnitude. If you want to be even more specific, then I will add here vector. Yes, magnitude of vector fx, magnitude of vector fy. All right. I am trying putting too many words in this, which is actually a simple concept. But what I want you guys to review, to get back into your memory, is the trigonometry of this. At this point, many people have this very clear, no problem at all. But some others may still struggle about this, sine, cosine, and tangent. So every time you have a rectangle here, a right triangle, where you have one of the angles 90 degrees, there will be two sides of the triangle that make up the 90-degree angle. That will be this side here and this side here are the angles that make up the 90-degree angle. And then you can talk about this angle alpha, or you could talk to the other one here. Let's talk about the alpha in this case here. If you're talking about the alpha angle, which is one of the other two angles in the triangle that are not 90 degrees, then talking about this angle, there is one side that is in front of the angle, which is called here I put an O for opposite side of the angle. And I put S here for the actual, so you know what? Let's change this S by A for adjacent. I don't know what is more clear for you guys. If A for adjacent or S for side. I don't know what you guys like better. S for side or A for adjacent. Adjacent. How do you pronounce that? Let's keep with the A, adjacent. I think I like it more, A, adjacent. So remember, the sine of the angle can be found as the ratio of the opposite side over the hypotenuse. Oh, I didn't mention that, maybe the most important. This other side of the triangle, which is the side that is opposite to the 90-degree angle, is called the hypotenuse. The hypotenuse of the triangle. We will be dealing with this the whole semester. I want to emphasize that if you have some kind of struggle with this concept, you have to review them because you need them all the time, and you have to be able to see this not as easy as you see it in this page, but in angles that are twisted, upside down, or hidden between among other elements of a drawing. And you have to be able to see which one is the rectangle, which one is the opposite side, which one is the adjacent side, in order to calculate the sine and the cosine. And also you need to calculate the tangent eventually, which will be the opposite side divided by the adjacent side. This is the tangent. Sometimes you have to find the angle, so you need to find this as the angle which tangent is that value opposite over, and let's put it A here, adjacent side. Or you can eventually, you might need to find the angle based on the arc sine function, the arc cosine function, or the arc tangent function that I have right there. Okay. Now, we are going to be talking about the rectangular components of the forces in 2D in the plane, usually on an XY plane. If you are going to find the components of a force in an XY pair, you can use, for example, in this case, I have this force of 800 newtons at 35 degrees right there. And if you refer this to the X and Y plane, the X component is going in the negative direction. So in many cases, it's going to be important this sign, if it's positive or if it's negative. This sign is important here. Same thing for the y-axis. It's important here that the y-axis is going to be positive going up. So when you calculate the components, if we are dealing with the signs also, you can calculate the sine of the angles. Like here, you can calculate the sine of 35 in order to find the components of the vector. Let's say you are trying to calculate the components of this vector here, fx, and the component of this here, fy. You can do this fx as f cosine of 35, but then you have to put the sign manually, right? You have to put the minus sign yourself, because the f is just the number 800, and the cosine of 35 is just whatever number is this, but it doesn't have a sign. Well, it does have a sign, but it's not this minus sign. Let's see, what is the cosine of 35? Cosine of 35 is 0.92. So you have here 0.819. But where this sign comes from? This sign comes from you. You have to know that this arrow is going to the left. So you have to put the sign yourself, and you have to be very careful about this. That's your responsibility. On the other hand, if you measure the angles starting always at the X positive, if all the angles are measured that way, the sign will be automatic. So if you measure the angles, all of them based on the positive X-axis, so the angle of this 800 Newton force is not 35, but 145. If you do that, then when you're going to calculate the X component, you will do F cosine of 145. You forget about the angles because it's going to be automatic. You say Fx is equal to 800. And if you calculate the cosine of 145, you go to your calculator cosine 145, and you get minus 0.819. See, the sign is automatic. All right. Okay. This is important. You have to be careful with the signs. If you don't measure the angles, all the angles with respect to the X positive axis, then the sign is your responsibility, and you have to put the sign yourself. Make sure that the sign of the components go tell you the direction of the component in the X or Y direction, positive or negative direction. All right.
We could also just work with the magnitude and then at the very end indicate whether it's in the negative or positive I or J direction, right?
The sign is important. The sign is important. If you want to do it automatic, the way will be measuring angles with respect to X plus. If you don't want to do it that way, because sometimes you get these big angles that are kind of awful and not very nice to visualize, then you look what is the direction of your forces and you put the sign yourself. Usually when you are doing a computer program, you use the automatic way. Because in the computer, you cannot, if you do a computer program, you cannot put your hands inside the program when you are running it in order to assign the signs manually. The computer has to be able to find everything automatically. So all the angles have to be determined inside the program, inside the coding, in such a way that all the angles are referred to the X plus axis. All right. Well, there is not much to say about this. The concept is really, it's kind of simple. You have the components of the vector in the XY plane, rectangular components. If you have the vector, the components are the magnitude of the vector times the sine and the cosine going the X, the Y direction. Eventually, it's not X and Y, it's just like U and V or M and N. But as long as those directions are 90 degrees, those are rectangular components, and you will calculate the magnitude of those components using sines and cosines. Sometimes you have the components and you have to find the resultant. That happens all the time. It's the opposite problem. So in that case, what we'll do here, if you have the components Fy and Fx, then you need to find the resultant. When then the resultant X will be by Pythagorean equation, right? And this is not new for anybody, right? Pythagorean equation. How you find this angle? Okay, well, you do alpha equals tangent minus 1 of Fy over Fx, right? Okay, so this is an example here. Well, this the example that I was looking at there, just with numbers. We have the force of 800 newtons right here, and we need to find the components. So and then we go if the component in the X direction is here we are putting manually the sign F, then the magnitude of the force 800 and the cosine of 35, and you get the minus 655 newtons, right? And if we want to write it in this notation, you have here this is the vector in the direction X. In the typing of this document, I see this kind of ball, so this is a vector, right? Is given by the sign that gives me the sense in which the vector is running, so it's going to the left. The magnitude of the vector, and this I will be the direction of the vector Fx. It has to be I because it's in the X direction. This is the notation for the Y components. The vector in the Y direction. The positive is telling me that it's going in the up direction. The magnitude of the vector and the direction of the vector. J is the direction in the vertical direction. So here we are expressing the vector F as a function of its components. And here is the original definition of components. The components are two vectors that if you add them together, This is the summation, right? This is minus something plus something. This is the summation of two things. Those two things are the x component and the y component. So here what I'm saying
Top of
is,
it.
sorry?
Why F he doesn't have an arrow? Does mean a vector? Should be an arrow in the top.
Yeah,
And G, I and G.
because as I said, this is a way you can see it in the textbook. When they are in bold, bold means vector.
Okay, I got you.
But yeah, but that's what I said. When you are writing, you cannot do bold and regular characters. So if I
Yeah.
am going to do this in a homework, I don't do it like this. I will do like this. In a homework, when
Yeah,
I'm writing
there
with
you
my
go.
hand, I will do like this.
Mm-hmm.
That would be better by hand.
Yep.
Okay. Any questions so far?
So you don't mind which kind of vector notation we use as long as it's correct?
As long as it's clear, right? As long as it's clear.
Okay.
Because in writing you cannot do the bold stuff, so it's better to put the little hats to make sure that this is a vector. This is not a vector. This is a magnitude. To differentiate magnitude or vectors. If you want to make sure and you want to state very clearly that you are talking about the magnitude of the vector and not the vector with all its components, because remember, a vector has several properties. In general, magnitude, direction, and sense. That's a vector. Magnitude, direction, and sense. If you want to talk about a vector in writing and you want to make sure that everybody understands, I will put the little arrow on top. That's a vector. This is a vector. And if you are talking just about the magnitude for certain explanation that you are doing an equation something, and you want to make sure you are not talking about the vector, but just the magnitude, the number, how big it is, then if you want to be very clear, you have to do it like this. It's kind of, there is no doubt. There is no doubt that this is just magnitude. Just magnitude. And this is the whole vector. The whole vector. Okay? If I write this, what do you understand if I write this? What do you understand if I write this?
1.
Just a number 1. It's just a number 1. Right? It's just a number 1. It doesn't have direction, it doesn't have anything. What if I do this? If I do this, what do you see? What do you understand if I write this? What do you see?
A vector.
Not only a vector, you will see a vector of magnitude 1 going up, right? This will be a vector of magnitude 1 going up. What if I write this? What is this?
Going left one unit.
I will see a little arrow going to the left of 1 unit. You see the whole thing. You see something up in the air, moving to the, not moving, pointing to the left, and a magnitude 1. All right. Okay. We're going to do these 2 examples. Example here, example number 1. It says here, a man pulls with a force of 300 newtons on a rope attached to a building as shown. You guys see the little guy, right?
Yeah, we see it.
Thank you. Okay. What are the horizontal and vertical components of the force exerted by the rope at point A? So here at point A, the rope is going to be applying a force in this direction. and the force is 300 newtons, right? So now here on the right, we see the diagram. And they already draw for, I'm going here very slowly so you guys have time to draw it on your paper. So now I have the axis X positive to the right and Y positive going up. And then we have some dimensions here. It says that the building is kind of 6 meters up from the point where the guy is holding the rope to the roof, or the place where the cable is attached at the roof. And we have the horizontal distance between the building and the guy is 8 meters. So we don't have the alpha angle here, but we have a way to find it. We can do several things. We can find the alpha angle. We can do many things here.
Tangent.
So we can find the alpha angle by the arctangent, right?
Mm-hmm.
Arctangent of 6
over 8.
right? We can also do something different, but that's a good thing to do. You can do the arctangent, and once you have the arctangent, then you have the angle, and then you can find fx as f cosine alpha and fy as f sine alpha, right? That's a way to do it, right? Another way to do it will be, I hope everybody understands. Let's go over that method very quickly again. Alpha will be equal to tangent minus 1 of 6 over 8. Whatever that is. We can do it very quickly here in the calculator, right? Arctangent
36.87.
36.87. 870, right? If we are doing 5 digits, because it's an intermediate calculation, right? I hope many more people is doing it in your own calculators at home, so you verify these numbers. This is an intermediate calculation, so I am doing 5 significant digits. Now that we have alpha, we can find fx as 300 cosine of 36.870 degrees, right? Whatever that is. And we can find
240.
fy equals to 300 sine of 36.870, right?
180.
180?
F of y is 180, yeah.
180. And you said fx eventually before you said it?
It's 240.
240.
Oh, but Fy is different directions. So we even put like minus.
Yes, I don't want to. You said what did you say for 300?
240.
240.
Yeah, because it was like 239.999.
So 3 digits will be 240. Okay. This is the magnitude. This is the magnitude of fx here. This is the magnitude of fy here, right? If we want to write it as, so the vector f, we can write it as 240. Oops. 240. Do I have to move
I.
240 newtons I positive minus
Negative.
180 newtons J, right? Negative, right? That will be the force given as a function of its components, right? And alpha equals 36.9 degrees. Since if this is the final answer, I can put this. Well, this is not an answer because they gave us the dimensions. This will be the answer here, the components of the vector. We can write like this, or we can write it like this. Fx equals minus, sorry, Fx is positive. Fx is 240 newtons, and Fy is What did it go?
180.
180. Minus 180 newtons. Ah, I don't have enough space here. I, J. Okay. There is another way to do it. Because we could, that's probably what they did here. Well, let's go down here. There is another way to do this, very similar way. I don't know if that's what they did here. Let's see, there it is. Is the fact that, let's increase the size. Is the fact that if you know these dimensions, then you can find this dimension from A to B. You know that this dimension from A to B, let's call it, well, this is the, let's call it here, AB. I need to reduce the size of this. The distance from A to B is equal to the square root of 6 squared plus 8 squared, right? So this is equal to 10, right? So this is 10 here. The distance from A to B is 10. So we know that for the angle alpha here, sine of alpha is equal to 6 over 10, right? And we know that cosine of alpha is equal to 8 over 10. So then we can use that. We don't need to find the angle. We can go directly as, again, we have the force. Let's put it here, the force, 300 newtons. And then we have here the x component, Fx, and the y component, Fy. And we know that the Fx component is equal to 300 cosine alpha. But we know that the cosine of alpha, we have it here, is 8 over 10. So this is 3 times 6 is 24. So 240. And Fy is equal to 300 sine alpha equals to 300. And we know that sine of alpha is this right here, 6 over 10. 6 over 10. So this is 3 times 6, 18, 110. So there you have it. Fx equals 240 I of y equals minus 180 y. Okay? Easy? Easy?
Yep.
All right. Okay, here is more or less the same thing. Let's do the signs. Well, if you want, again, this is the final expression of the vector f as a function of its components. We mentioned the tangent. We also mentioned this stuff, right? The tangent of the angle. Well, similar stuff. What else? Now, what happens if you want to add forces using components? Let's say you have these 3 forces, and you want the resultant of 3 forces. Using this method is really easy, because then you have each force. You get the components of the force in the x and y direction. So P, this is P, this is S, this is Q. You get the components of each force in the x and y direction. And once you have all the components in the x direction, then you add these 3 in the x direction, and you have to be very careful about the signs, because these 2 are positive and this one is negative, right? So you will get this number positive plus this number positive minus this number positive. So the summation of these three forces will give you this resultant here in the x direction. Same thing you do in the y direction. So you will have these three components in the y direction, and you do the summation of these three. You have this number plus this number minus this number, and then you get as a result this resultant in the y direction. So the final resultant, or which will be the summation of all these three forces, will be getting the resultant of these two, and the resultant of those two is this graph here, and you have already the Pythagorean, right? The resultant will be magnitude of rx squared plus ry squared, right? That's the magnitude of the resultant, the magnitude of the resultant. And the direction will be given by this angle here. And this angle here, you get it by doing the arctangent of ry over rx, where this is ry and this is rx, right? And in this case, there is no ij, nothing. You cannot say something like r has some kind of ij. You don't have it. So you have to refer to the magnitude, and you have to mention the angle, and you have to be very specific. You're going to say 30 degrees with respect to the x positive, or 30 degrees to the right of the y positive. You have to express with your words what is the direction of that vector r. Or you can express the vector r as a function of the components. That's what you have down here. No, this doesn't want to go down.
We could just draw the axis on there, right? So we could just extend one of the arrows and call it x or y.
Like a picture is worth 1,000 words. The best thing would be to try to do a little drawing, right? You do like this, and you say 340 newtons. 65 degrees. That will be the best way to show exactly what is the direction, right? Or you can show, let's see if they have it here. I don't see it like this. So you can do, the resultant is rx I plus ry j. And it will be useful if you put here the total magnitude, let's say 340, right? That will be like a nice. So what they are showing here is just how you calculate those summations. This summation of forces in the x direction is the summation of these three components. These are the components of each one of the forces in the x direction, and how you do the summation. And same thing here for the y direction, right? I'm gonna put these notes on the blackboard. This example is just exactly what we did right here, exactly what we do here with letters, but this is done here with numbers, and the concept is really simple, right? You get the components, you see your sine and your cosines. You see the components right here. These components is just by using the sines and the cosines. Same here, the sine and the cosine. All the calculations are shown in this graph here. And then they just put it here in a nice table where you do the summation of all the x components and the summation of all the y components. And then here is showing the resultant as a function of the components. Here you calculate the angle as ry over rx, the way we did up there. And here, well, forget about this one. This is just silly. The best way to find the resultant here, I wouldn't do it like this. I would do the resultant, the magnitude of the resultant at the square root of Rx squared plus Ry squared. That's the way I will do R in order to get this. And that's a nice way to write. So you please guys go over this one a little slower. There basically there is everything is here because all the equations of sines and cosines are here inside the graph, and then all the numbers go to the right into that table to get the summation, right? Okay, please go over that one, finish that one, finish taking a look at that one, and you should be able to finally understand all these concepts here. I suggest you go over these examples on your own from the book. Go over those 3 examples slowly. They are explained in different ways. Either use the sine, the cosine directly from the angle using your calculator, or using the concept that the sine is opposite over hypotenuse, or the cosine is adjacent over hypotenuse, or you can use just the cosine and the sine from your calculator, right? Either way. And then please go over those examples so you get to dissipate any doubts that you have about this. Make sure you review, you don't have any problem about what is sine, what is cosine, and what is tangent. Make sure you master that completely.